Workers serving under Pharaoh Joser are nearing completion on one of the ancient world's largest construction projects, a pyramid. We may finally understand how the ancient Egyptians actually cut granite, not just another theory or the same explanation Egyptologists have, repeated for more than a century, but a method supported by physical evidence. And the breakthrough didn't come from a traditional archaeology lab. It came from a tribology research facility using a scanning electron microscope. Their material scientist, Dr. Masoud K. Bey, someone who had never worked in Egyptology, closely examined the cut surface of a 4,000-year-old granite block. What he discovered was completely unexpected. Embedded in the surface were traces of corundum, a form of aluminum oxide. This is the same extremely hard mineral that creates rubies, sapphires. On the MO hardness scale, corundum ranks at 9, making it one of the hardest natural substances on Earth, second only to diamond. Basically, on the MO scale, you have, and that's a hardness scale, you have diamond. And the next one is aluminum oxide. That's one reason, pretty much, everybody uses aluminum oxide. And that's one reason the warranties are so good. Its presence suggests that the ancient Egyptians may have used this incredibly hard material as an abrasive too. Cut and shaped granite, revealing a level of technical knowledge far more advanced than many people previously believed. It was hidden deep inside the ancient, cutting grooves exactly where Egyptologists had always expected to find nothing more than ordinary sand and traces of copper. Instead, they found something entirely different. Just one, Discovery 1. Mineral and decades of academic certainty suddenly began to fall apart. This is the evidence that Graham Hancock pointed to. And by the Ezaton end of this video, you'll see exactly what was uncovered. But here's the real twist. The pyramids themselves may not be the greatest mystery of ancient Egypt. Most of those massive structures were built from limestone, and historians have a reasonable understanding of how they were constructed. The real puzzle, the one that has baffled engineers, archaeologists, and stonemasons for more than a century, is granite. Granite ranks around 6 to 7 on the MO hardness scale. It's made of tough minerals like quartz, feldspar, and mica, materials so resistant to cutting that even today, shaping granite is incredibly even when a machine with modern diamond-tipped power tools, working with granite is slow, expensive, and extremely demanding, which makes the precision granite work found in ancient Egypt even more puzzling. And yet the ancient Egyptians seem to shape it almost as if it were clay. The king's chamber inside the Great Pyramid of Giza is built entirely from massive granite blocks, some weighing more than 70 tons. At the nearby Valley Temple of Khafre, enormous granite stones are fitted, together with joints so precise that you can't even slip a razor blade between them. There are also statues carved from single pieces of granite, with surface details so smooth and refined that they almost appear to be machine-made. Then there are the drill cores, discovered at ancient sites. These cores show spiral grooves cutting deep into solid stone at feed rates that make modern engineers pause in disbelief. When Christopher Dunn, a manufacturing engineer with more than 40 years of experience in precision machining, examined these granite artifacts, his reaction was immediate. The level of accuracy he observed was extraordinary. He noted surfaces that were flat to within 1/1000th of an inch across, several meters, and drill holes that remained perfectly circular throughout their entire depth. According to Dunn, these weren't just impressive examples of ancient craftsmanship. They looked industrial. After spending his career working with CNC machines and high-precision components, he concluded that the work done by the ancient Egyptians in granite matched, or in some cases even exceeded, modern manufacturing standards, not roughly, not approximately, but with remarkable precision. So what's the official explanation? According to the traditional view, the ancient Egyptians used copper sores with sand as an abrasive, along with heavy dolerite pounders and a lot of patience. But there's a major problem with that idea. Copper ranks only about 2.5 to 3 on the MO hardness scale, while the quartz inside granite ranks around 7. when you try to cut a much harder material using a softer tool. Even with abrasive sand, the tool usually wears down or fails long before the stone gives way to test. This Dennis Stocks from the University of Manchester conducted years of experiments using copper tools and sand on granite under controlled conditions. The results were slow and frustrating. The cutting progress was often measured in fractions of a millimeter per hour. The copper tools wore down quickly, and the cuts that were produced were rough and uneven. Nothing like the smooth, precise surfaces seen on ancient Egyptian artifacts. Stocks himself admitted that the experiments raised more questions than answers. Dorite. Pounding can shape granite, but it works at an extremely slow pace. Even forming a small granite surface through repeated hammering can take hundreds of hours if you scale that up to something like the granite used in the king's chamber of the Great Pyramid of Giza. The labor required would reach millions of hours just for the granite work alone. And none of these methods explain the incredible precision found in these structures. Some granite surfaces are flat to within 1/1000th of an inch. Drill holes stay perfectly circular from top to bottom. Saw cuts run straight and parallel for several meters. That kind of accuracy isn't something you would normally expect from simple rocks and soft copper tools. For decades, Graham Hancock kept pointing this out. His argument was simple. Some of the physical evidence doesn't seem to match the conventional explanation. According to him, something important is missing from the story. But the response from mainstream archaeology was usually the same. Hancock isn't formally trained in archaeology. His ideas are considered fringe. His questions, many argued, didn't deserve serious attention. So for years, he was largely ignored until something new appeared, something that may have filled in the missing piece. And that discovery is the reason you clicked on this video. This is where the story takes a surprising turn. In 2022, Graham Hancock partnered with Masoud Garb, a scientist who studies tribology at a major research institution. Dr. Garb wasn't involved in the long-running debates about ancient Egypt. He's approached the subject simply as a scientist interested in solving a technical puzzle. Together, they received permission to examine ancient Egyptian granite artifacts using powerful laboratory tools, including scanning electron microscopy and energy, dispersive X-ray spectroscopy. These instruments can analyze surfaces at an incredibly small scale, revealing details far beyond what any normal microscope can see. At first, Dr. Garb expected to confirm what Egyptologists had been saying for decades. The common explanation suggested that the granite had been cut using copper tools and sand as an abrasive. So he assumed he would find traces of sand grains and copper residue, the chemical signs of that process. But that's not what appeared under the microscope. The wear patterns didn't match the marks left by sand. The scratch patterns looked different. And when Dr. Garb examined the tiny particles embedded in the ancient cutting grooves, he noticed something unexpected. Inside those 4,000-year-old grooves were traces of corundum, a mineral that ranks 9 on the Ertmem hardness scale. That makes it one of the hardest materials found in nature, second only to diamond. In modern industry, synthetic corundum is often used as an abrasive for cutting and shaping extremely tough materials. And yet here it was embedded in stone cuts made thousands of years before the rise of the Roman Empire. But there's another important detail. Corundum does not naturally occur in Egypt, in forms suitable for large-scale use. The closest significant sources are in regions that ancient Egypt did trade with. Still, simply having access to the mineral wouldn't automatically mean people understood how to use it effectively. Recognizing corundum's hardness and deliberately grinding it into an abrasive mixture for cutting granite would require careful experimentation and a solid understanding of materials. Dr. Garb was very clear about this point. Using corundum properly means knowing how to grind it into specific particle sizes and how to apply it in the cutting process. In other words, it wouldn't be something discovered by pure accident. This is where the story starts to feel like a lesson in material science. If discoveries like this are changing the way you think about the ancient world, consider subscribing. We explore stories that dig deeper into history and look at the evidence behind claims that challenge the usual explanations. The implications of the finding were immediate. If the ancient Egyptians were intentionally obtaining corundum through long distances trade, grinding it into carefully sized particles, and mixing it into cutting slurries, then they may have understood advanced material properties far better than traditional interpretations suggest. But finding something under a microscope is evidence, not final proof. Graham Hancock understood that difference. If the idea was going to be taken seriously, it had to be tested in real experiments. So in early 2023, he helped organize controlled trials in a workshop using granite blocks, copper tools, and several different abrasive materials. Stonemasons and materials scientists worked side by side, testing three main possibilities. Sand, the traditional explanation, quartz powder, which is slightly harder and was available in ancient Egypt. A corundum quartz slurry, the new hypothesis. The results were surprisingly clear. Using copper with sand produced cutting speeds of about 0.5 millimeter. It was extremely slow. The copper wore down quickly, and the surfaces were rough. With copper and quartz powder, the speed improved slightly to around 0.8 millimeters. A small improvement, but still nowhere near the level of precision seen on ancient granite artifacts. Then they tried the corundum mixture. The cutting rate jumped to over 3 millimeters per hour, roughly 6 times faster than sand. Even more interesting, the copper tools lasted far longer and showed much less wear. For the first time, the experimental results began to resemble the kind of efficiency and precision seen in ancient Egyptian granite work. The results were striking. The cuts became smooth, clean, and remarkably accurate. But the most surprising moment came during the drilling tests. The team produced core samples with spiral grooves that looked exactly like the ones found in ancient Egyptian drill cores. These are the same spiral patterns that had puzzled engineers and researchers for decades, and the same ones that the traditional copper and sand theory had never been able to reproduce. Yet here they were, freshly cut into modern granite during the experiment using methods inspired by ancient techniques. A veteran stonemason named Nick Giza, who had spent decades working with granite, described what that moment felt like. According to him, everything suddenly made sense. Instead of the copper tool struggling against the granite, the tool began acting more like a guide for the abrasive. The cutting became smoother. The speed increased dramatically, and the wear on the copper dropped significantly. He explained that for the first time in his entire career, standing in that workshop and watching the process unfold, he could actually imagine how ancient craftsmen might have worked with granite so effectively. But the experiments revealed something else as well. Using a corundum slurry wasn't simple or accidental. It required real skill. The mixture had to maintain a very specific consistency during the cutting process, or the efficiency quickly dropped. Managing that balance demanded careful control and practical experience. If the mixture became too thin, it quickly lost its cutting power. If it became too thick, it clogged the cutting groove and slowed everything down. The pressure had to stay steady. The temperature needed to be controlled, and every small variable made a difference. In other words, this process required highly skilled craftsmen who truly understood the materials they were working with. It would have taken years of experience, knowledge passed down from master to apprentice, refined over generations. That's exactly the kind of specialized workforce you might expect from a civilization capable of building monuments like the Great Pyramid of Giza. By this point, 3 different lines of evidence were pointing in the same direction. Microscopic analysis of ancient granite cuts experimental replication in modern workshops. Material science. Data explaining how the abrasives behave. But Graham Hancock already suspected what might happen next. He had experienced similar reactions before. When he presented the findings in late 2023, he chose an unusual venue, a materials science conference, not an archaeology meeting. The audience was filled with engineers, physicists, and materials scientists who tend to evaluate evidence based strictly on data and experimentation. The response there was largely positive. Researchers in the room understood that the results were worth serious discussion. For example, James Harold, who has studied ancient Egyptian quarrying for decades, has pointed out that abrasive slurries rarely survive in the archaeological record. In other words, the absence of direct remains of such mixtures doesn't necessarily mean they were never used. For many scientists in the room, the new evidence opened the door to reconsidering how ancient craftsmen may have worked with some of the hardest stones in Egypt. According to researchers, traces of corundum, embedded inside ancient cutting marks, could be some of the strongest physical evidence we may ever find. But this is where the discussion becomes more complicated. When the findings began circulating among Egyptologists, the reactions were mixed. Some archaeologists acknowledged that the idea was plausible and asked reasonable scientific questions. For example, how much corundum would have been required for large-scale stonework? Is there historical evidence of corundum being traded during the relevant Egyptian dynasties? Could the traces discovered in the stone possibly come from later contamination? These are the kinds of questions that good science naturally raises. However, not everyone focused on the scientific details. In some cases, the conversation shifted toward the person presenting the idea, Graham Hancock. Hancock has long been a controversial figure in archaeology, largely because of his earlier book, Fingerprints of the Gods, which proposed alternative interpretations of ancient history. For decades, many scholars have criticized his work and labeled his ideas as outside mainstream research. Because of that reputation, some critics reacted not to the new data itself, but to who was presenting it. Instead of debating the evidence first, the discussion often centered on Hancock's long-standing position as an outsider to traditional academic archaeology. Their stance was direct and uncompromising. For some critics, Graham Hancock being involved was enough to cast doubt on the findings, regardless of the scientific work behind them. In their view, the association itself made the research difficult to accept. According to this perspective, the data, the experiments, and even the successful replications were overshadowed by the name attached to the project. Hancock addressed this issue during an interview in 2024. He said that some Egyptologists told him that even if the corundum explanation turned out to be correct, they believed he should not be the one presenting it. In their opinion, his lack of formal archaeological training disqualified him, even though the work also involved qualified scientists and reproducible experiments. Hancock argued that the disagreement was less about the evidence and more about who has the authority to shape historical narratives. But scientific evidence, in principle, stands or falls on its own merit, and the corundum hypothesis has gradually attracted attention in fields where the technical aspects are most relevant among engineers, material scientists, and some archaeologists who are willing to evaluate the data independently of its source. It's important to be clear about what this discovery does and does not mean. Finding traces of corundum and successfully reproducing the cutting results does not automatically confirm every theory Hancock has proposed in the past. His broader ideas about lost ancient civilizations are still debated and remain controversial. However, on one specific question, how the ancient Egyptians were able to cut granite with such remarkable precision, the new evidence has strengthened the argument that more advanced abrasive techniques may have been used than previously assumed. In other words, the discussion is far from over, but the evidence has opened the door to re-examining how ancient craftsmen might have achieved results that still impress modern engineers today. If the ancient Egyptians intentionally used corundum-based abrasive slurries, it could significantly change how we understand their technological abilities. It would suggest they understood mineral hardness far better than many historians once believed. It would also imply that they maintained long-distance trade networks to obtain materials that were not naturally available in the Nile Valley. On top of that, they would have needed the knowledge to process the mineral correctly. Grinding corundum into specific particle sizes and mixing it into slurries with the right consistency for cutting stone. That kind of process begins to look less like simple trial and error and more like a form of early materials science rather than being primitive builders. It would highlight just how skilled and knowledgeable these ancient craftsmen were. And the discovery raises an important question for researchers. If something like this could remain unnoticed for so long, an entire abrasive technique hidden in stone surfaces examined by thousands of experts, what else might still be overlooked? How many ancient methods have been dismissed as impossible simply because the right tools or approaches were never used to investigate them? In a tribology laboratory, Massadgarb studied microscopic images of granite cuts made more than 4,000 years ago and noticed traces of corundum where few people had ever thought to look. In a workshop experiment, Nick Geiser tested a copper blade with a corundum slurry against a granite block and watched it cut smoothly quickly, and with impressive accuracy, demonstrating how such a technique might have worked in ancient times. Meanwhile, Graham Hancock had spent decades raising questions about ancient technologies and historical assumptions. Over the years, he was often criticized by scholars, challenged in academic discussions, and dismissed by many researchers. But eventually, he and collaborating scientists presented experimental results and physical evidence that brought new attention to the question. And that evidence has reopened a conversation that many thought had already been settled. This wasn't just a theory. It wasn't speculation or a guess built on imagination. What researchers were pointing to was physical evidence. Microscopic traces preserved in stone that had survived for thousands of years. Those traces were studied using modern instruments analyzed through material science and tested through experimental replication by scientists who had no stake in defending any historical narrative. The picture that began to emerge was remarkable. The evidence suggested that the ancient Egyptians may have cut granite using corundum-based abrasive slurries, a technique far more advanced than the simple copper and sand explanation that had long been repeated in textbooks. If that interpretation is correct, it reveals a technology built on a surprisingly deep understanding of natural materials. Corundum is one of the hardest minerals found in nature. On the MO hardness scale, it ranks 9 just below diamond. Modern industries still use synthetic corundum as an abrasive when cutting extremely tough materials. Finding traces of it embedded in ancient cutting grooves suggests that Egyptian craftsmen may have understood exactly how powerful such an abrasive could be. But using corundum effectively would not have been simple. It would require obtaining the mineral through long distance trade networks because large natural sources do not exist in the Nile Valley. That means the Egyptians would have needed established connections with distant regions where the mineral could be acquired. Trade routes would have carried not just goods, but knowledge. Knowledge about which minerals were valuable and why. Once obtained, the mineral would have had to be processed carefully. Corundum would need to be crushed and ground into particles of specific sizes, then mixed with water or other substances to create a slurry that could flow through cutting grooves while maintaining enough abrasive power to grind away granite. Too thin, and the mixture would lose effectiveness. Too thick, and it would clog the tool and slow the cut. Managing that balance requires skill, patience, and experience. It is the kind of knowledge that develops over time, refined through practice, taught from master craftsmen to apprentices, and improved across generations. In other words, this wasn't the work of people struggling with primitive tools. It was the work of specialists who had spent years learning how to control materials that most civilizations would have found extremely difficult to work with. And when you look again at monuments like the Great Pyramid of Giza, the precision begins to make more sense. Granite blocks weighing dozens of tons surfaces, polished smooth joints aligned so tightly that even a thin blade cannot slide between them. These details hint at a level of craftsmanship that modern engineers still admire. For decades, Graham Hancock argued that the traditional explanation for Egyptian granite work did not fully account for the evidence. For many years, his ideas were heavily criticized, and his conclusions were often dismissed. But if the corundum findings continue to hold up under scientific scrutiny, they suggest that at least one of those challenges to the conventional explanation may have been pointing in the right direction. And that leads to a much bigger question. If historians and archaeologists could overlook something like this, an entire abrasive technology hiding in the microscopic traces of ancient stone surfaces, what else might we have misunderstood about the ancient world? How many techniques, tools, or forms of knowledge have been underestimated simply because modern researchers assumed earlier civilizations lacked the ability to develop them? History is full of surprises. Every generation of researchers brings new tools, new methods, and new ways of looking at old evidence. Sometimes those tools reveal details that were invisible before. In this case, the story may have been sitting in the granite all along. The evidence is in the corundum, and the corundum is in the granite. If discoveries like this change the way you see ancient history, if they make you wonder how much more there is still to uncover, consider subscribing. Because stories like this are only the beginning. And the deeper we look into the past, the more extraordinary the ancient world begins to appear.